Okay, very good morning, one and all. In the last classes, we discussed the importance of DPSK, differential phase shift keying, over BPSK and BASK. And we found a few drawbacks for the differential phase shift keying as well as the binary phase shift keying. So we can overcome some of the drawbacks by using differential encoded phase shift keying. So in today's class, we can discuss the differential encoded phase shift keying technique, so which has a lot of advantages over the traditional BPSK and DPSK, that is binary phase shift keying and differential phase shift keying. Now, if you observe the learning outcomes, we can be able to interpret the performance of differentially encoded PSK transmitter and receiver sections. So after completion of this topic, you can be able to analyze the performance of DEPSK. So generally the full form of DEPSK is differentially encoded PSK. So this is the upgraded version of differential PSK. So in sense, if you want to speak in sense of transmitter and receiver sections, you can call it as DPSK transmitter section, and it consists of BPSK receiver. So differentially encoded PSK consists of DPSK transmitter section and BPSK receiver section. Now please all of you observe the corresponding slide which is shown here. So in this we mentioned few drawbacks of DPSK as well as BPSK, and those drawbacks we can overcome using DEPSK. So if you observe the corresponding slide, please observe the first point. Already I told you that DEPSK, you can state the DEPSK system as a combination of DPSK transmitter and BPSK receiver. So in the last class, we found so many advantages for DPSK transmitter section. So what are the advantages of DPSK transmitter? See, in the last class, we discussed that DPSK transmitter section consists of differential encoder. Okay, so what is the advantage of this differential encoder? Simultaneously, you can transmit 2 data bits. So then what happens to our bandwidth? You can reduce it to FB. So you can reduce it to FB. So that's why the bandwidth of DPSK transmitter section. So you can generate the DPSK signal with less bandwidth because it uses differential encoder, which will compare the present data with the past differential encoded data. So if you are able to compare like that, then automatically simultaneously you are doing the transmission, 2-bit transmission. Okay, so that is the main advantage of DPSK transmitter section, whereby the bandwidth required for transmitting the DPSK signal is less. So already we discussed in the last class that the bandwidth of DPSK is FB. Because what is the general bandwidth of any MRA PSK? We defined it as 2FB by N. 2FB by N, where M is equal to 2 power N. Okay, or N is log M base 2. So if you do like that, based on the value of number of bits transmitted per symbol, our bandwidth will differ. So obviously we can state that as we move on going the upgraded versions of PSK, like 4 array PSK, 8 array PSK, 16 array PSK, and M array PSK. If you go like that, that is 2 power N array PSK, so automatically our bandwidth gradually decreases upon transmitting multiple number of bits via the channel. Okay, that is the main advantage of differential encoder used in the DPSK transmitter. And not only the bandwidth issue, our DPSK receiver generates the unipolar energized format signal. Unipolar energized signal. Once the unipolar energized signal is generated, once you generate unipolar energized signal, it consumes less power over bipolar energy. But already we discussed that in BPSK transmitter section, it will make use of bipolar energized signal. Once we use bipolar energized, obviously our bandwidth will, it needs a lot of power for transmission, because a bipolar energized has two levels, positive level, signal magnitude in the negative component. So that's why the power required for transmitting our negative magnitude is equal to that of positive magnitude. So almost all we can say that the bandwidth, the power consumption is more in BPSK transmitter over DPSK transmitter, because this is all due to the utilization of unipolar energized in DPSK transmitter. Already we discussed DPSK general format, okay, BK into AC cos omega CT, where BK is unipolar energized obtained from differential encoder. What about BPSK? It is B of T into AC cos omega CT. So what are the drawbacks of BPSK transmitter section? In BPSK, bandwidth requirement is 2 FB. And because it uses bipolar energized, it consumes more power. So that's why DPSK transmitter section is used instead of BPSK transmitter. Then why you are using BPSK receiver in DEPSK? So DPSK receiver section, okay, the working principle is same and you are effectively getting good data. But here bit error propagation is there. Already we discussed, it has high probability of error. It has high probability of error. Which one? DPSK receiver. DPSK receiver has high probability of error because you are not using synchronous carrier. Once you do not make use of synchronous carrier, what happens to our probability of error? It will increase. So not only that problem, here for example, if there is any single bit error for the entire sequence, if it exists, so whenever you receive the data, okay, so if there is any kind of single bit error, that error will be propagated throughout the entire sequence, because the transmitter section of DPSK uses our differential encoder. Okay, you will generate some signal, but DPSK receiver, what it will do? It will while receiving, for example, if there is any single bit error, that error will be propagated, because what you will do there, the phase of received data is compared with phase of received data but shifted one bit right. Okay, so that's why if you are able to compare the phase of a decay and a phase of shifted decay, where decay is the received signal, if you do like that, automatically our signal, our bit error, because of single bit error, the error gets propagated throughout the entire sequence. So that is the main drawback of DPSK receiver. That's why some of the researchers, they introduced differential encoded PSK that uses DPSK transmitter section and BPSK receiver. That uses DPSK transmitter section and BPSK receiver. So that's why differential encoded PSK is a combination of DPSK transmitter and BPSK receiver to overcome the drawbacks of BPSK transmitter and DPSK receiver. What are the drawbacks of BPSK transmitter? High bandwidth necessity and high power consumption. And what is the drawback of DPSK receiver? That is differential PSK receiver, high probability error. At the same time, because of, even though there exists single bit error, that error gets propagated throughout the entire sequence. This is about the importance, or you can say the how the drawbacks of BPSK transmitter and DPSK receiver can overcome using DEPSK. The full form of DEPSK is differential encoded PSK, differentially encoded PSK. Now let us move to the next slide. In DEPSK, so already I told you that DEPSK transmitter is almost all similar to DPSK transmitter section. So because DEPSK is a combination of DPSK transmitter section and BPSK receiver, but slight modification in the circuit they did. Okay, so please observe the DEPSK transmitter section. Here what they did, instead of here we are using differential encoder, but in this differential encoder, instead of XNOR, we are using XOR. Please remember, the differential encoder actually it obeys or it follows XNOR operation in DPSK. But here the basic difference between DPSK modulator and DEPSK modulator is both consist of differential encoder, but our DPSK modulator used XNOR operation, XNOR gate as a differential encoder, and here differentially encoded PSK transmitter, it's using XOR operation. It uses XOR gate to perform that operation. And later, upon comparing the present bit BK with DK minus 1, you can generate the differential encoded data. So for the first upcoming bit of BK, you don't have DK minus 1 because there is no past data. So that's why what you can do, you can take the DK minus 1, that is the first data bit. You don't have any output. So DK minus 1, you can take the arbitrary data. So BK is compared with DK minus 1 to generate DK. So here DEPSK transmitter is almost all similar to DPSK transmitter, or you can say modulator section. But what is the basic difference between DPSK modulator and DEPSK modulator? Same circuit, but instead of XNOR operation, here you will make use of XOR gate. This XOR gate performs the operation. Now, any one of the student tell me the operating principle of XOR. So actually in DPSK we used XNOR operation. If for same data bits the output is 1. For different data bits, that is when BK is not equal to DK minus 1, output is 0. Can any one of you tell me what is the operation of XOR gate? Any one of you kindly respond. What is the general operating principle of XOR gate? Because in DEPSK, XOR gate is used in differential encoder. Any one of you?
When inputs are different, output is 1, madam.
When inputs are different, output is 1. So how many? Okay, you tell me what are the inputs?
0, 0.
Okay,
0,
here you can say directly in terms of BK and DK minus 1.
Yes, madam.
If BK not equal to DK minus 1, what is the output? DK?
1.
DK is 1.
1.
Okay, very good. When BK is equal to DK minus 1?
0, madam.
0. Now, when BK is DK minus 1, how many possibilities are there? 0, 0, or both can be?
1.
1. And BK not equal to DK minus 1, what are the possible combinations?
1, 1, 0, 0.
Yes, very good. Thank you, Ma. Thank you. So when BK not equal to DK minus 1, output is DK, that DK is equal to 1. When BK is equal to DK minus 1, output DK is equal to 0. So please identify the basic difference between the DEPSK transmitter section and DPSK transmitter section. In DPSK, XOR gate is used. In DPSK, XNOR gate is used as differential encoder, but that XNOR is replaced by XOR gate in DEPSK transmitter. Okay. the output of the differential encoder is, what is the output now? Here you can observe the output as dk. Here you can observe the output as dk. So the output of differential encoder is dk. That dk is applied to the multiplier section, and as usual the dk is multiplied by carrier component. So from this, almost all the principle is same as that of DPSK transmitter. So what is the working principle? Bk is compared with dk minus 1 using XOR gate. The output is dk. Now the dk is multiplied with carrier. Carrier is AC cos omega ct. Please always remember that here dk is unipolar energized, because you will get dk as either 1 or 0. So that's why you can overcome two problems by using this DEPSK transmitter section. So what problems you can overcome here? So because simultaneously you are comparing two data bits, that is bk and dk minus 1. Mean that you can say that you are transmitting two data bits, so the bandwidth gets reduced. And second advantage is, here you are using unipolar energized as input to the multiplier. Once unipolar energized is used as one of the input to the multiplier section, our power consumption can be, you can reduce the power consumption. Now dk is multiplied with AC cos omega ct. So dk into AC cos omega ct. See, in the case of DPSK, the output is dk into AC cos omega ct. In case of DEPSK also, it is same as dk into AC cos omega ct. But the sequence is not same. Actually, we mentioned here as DPSK, but DPSK signal is not equal to DEPSK. Here this is obtained by using XOR gate, and DEPSK is obtained by using XOR gate, and our old technique, that is DPSK, is obtained using XNOR gate. Okay, so the equation is same, dk into AC cos omega ct, but dk is obtained from XOR gate, not from XNOR gate. Okay, but dk is unipolar energized. So what is the output of DEPSK modulator section? dk into AC cos omega ct. It is similar to DPSK, but dk is a unipolar energized that is obtained from XNOR gate, not from XNOR gate. It is from XOR gate. Okay, so please identify the basic difference between DEPSK transmitter and DPSK transmitter. Instead of XNOR, we are replacing it with XOR. So dk is obtained using this XOR gate. So dk into AC cos omega ct. Okay, so finally DEPSK transmitter section generated the modulated signal as dk into AC cos omega ct, where dk is obtained from XOR gate. dk is the magnitude, which is a unipolar energized obtained from XOR gate. So other than that, the working principle is same as that of DPSK. Now let us move to the next slide. See, already we have seen the DPSK transmitters operating principle. Here you can say the DPSK transmitter operating principle. Okay, so the output of differential encoder, already I told you that it is unipolar energized. What is the output? It is represented as dk. And now that is applied to the product modulator. The product modulator multiplies the unipolar energized with the sinusoidal carrier. What is the sinusoidal carrier? AC into cos omega ct. AC into cos omega ct. Upon multiplying the unipolar energized, that is dk component, with AC cos omega ct, you can get the output as dk into AC cos omega ct. The equation looks similar to DPSK, but here dk is obtained by using XOR principle, instead of XNOR principle. Now, if there is no transition between present and past encoded data, the differential encoder output is 0. So what is the principle principle of XOR gate? Already we discussed that if the input is same, that is when Bk is equal to Dk minus 1, our output is 0. For same data, for same inputs, differential encoder output is 0. For different data, like one is 0 and other is 1, then that occurs when Bk not equals to Dk minus 1. So what can be the output? The output is 1. So for different data, output is 1, and for same data, the output is 0. So you may get a doubt why we replaced XOR gate. We have already XNOR gate. Why we replaced? So because you can see the receiver. So the receiver also, once again, we'll to compensate this XOR gate used at the transmitter, even at the receiver, we'll make use of one XOR gate at the receiver section to compensate the XOR used at transmitter. Okay, that's why XOR gate is used at the transmitter section. One more XOR is used at the receiver. You can see the circuit. Okay, so I think DEPSK transmitter, is it okay to everyone? Can we move further? Please, one of you respond. Can we move further? Is this DEPSK transmitter okay?
Yes, ma'am.
Same, ma'am.
Okay, ma. Okay, thank you. Let us move to the next slide, where you can see the DEPSK receiver section. Please observe the DEPSK receiver. Please observe the circuit. Now, any one of you, please tell me, is there any difference between the DEPSK receiver and we said that it is almost all similar to BPSK receiver. So BPSK is a coherent receiver. I think you can remember the circuit of BPSK receiver. So many times I mentioned regarding this circuit, BPSK receiver. Now, please observe this circuit and tell me what are the additional elements used in DEPSK receiver compared to BPSK receiver section. So we identified the difference between DEPSK transmitter and DPSK transmitter. Now please tell me what is the fundamental difference between DEPSK receiver section and BPSK receiver.
Usage of XOR gate, ma'am.
Yes, very good. So here we are using XOR gate at the receiver section to compensate the XOR used at the transmitter. Okay, now please observe the DEPSK receiver section. Please observe the circuit carefully. So what is the input to the circuit? Noisy DEPSK transmitted signal. So all as usual to the BPSK receiver, but here the data is DK. Instead of bipolar, we got it as unipolar. So DK into AC cos omega CT. But what is theta? Already we assumed the same in BPSK receiver. Theta is the phase variation that occur due to the noise present in the channel. So what is theta? Theta is the phase variation that occur due to the noise present in the channel. We'll focus only on the phase variation because for DPSK, for phase shift keying especially, we don't have amplitude or frequency variation. We'll have only phase variation. So we'll focus only on phase. So that's why plus theta we assumed, okay, as we assumed plus theta as the phase variation that occur due to the noise present in the channel. So what is the received DEPSK signal? Transmitted signal is DK into AC cos omega CT. Received is DK into AC cos omega CT plus theta. Okay, plus theta you got. Now this signal is applied to the coherent carrier generator. Already we discussed in BPSK receiver the importance of coherent carrier generation using these three sections. We discussed it as that these three sections, square law device, band pass filter and frequency divider by 2. These three sections can be able to generate stable coherent carrier. Stable coherent carrier. That's why we are using the coherent carrier generator at the front end of our section. Now, in BPSK receiver, we have one problem due to the square law device. What it will do? It will square the upcoming signal. Once it square, in BPSK, the input is B of t into AC cos omega ct, where B of t is plus or minus 1. So for minus 1, if you square, you will get the same data as plus 1. Okay, but here that kind of problem do not arise because here decay is unipolar. That may be either 1 or 0. If you square 1, you will get 1. If you square 0, you will get 0 only. So that problem here you don't exist. What is that problem called as? Polarity problem. So we call that as polarity problem. So that polarity problem in BPSK you can overcome using DEPSK. How you overcome? By considering the unipolar energized signal. If you consider it as bipolar energized, then automatically once you square the signal, our signal gets squared. Then B of t, if you square, the output is always positive. But here, if you square, we don't have any such kind of problem. The polarity recognition, there is no need because it has only one polarity. And for 0, the output is 0. Okay, so that polarity problem due to the square law device from BPSK receiver, we can overcome because you are assuming the input as unipolar energized. Now, the output of square law device is applied to the band pass filter frequency divider. The 3 sections will generate the coherent carrier. So almost all it follows the same principle. Anyhow, we can discuss it here, but the principle is same. Next, that is applied. Next, the coherent carrier generated by this section is applied to the synchronous demodulator. This synchronous demodulator acts as a multiplier, which it multiplies the DEPSK signal with the generated synchronous carrier. Here the synchronous carrier is generated based on the received signal. So the received signal is dk into AC cos omega ct. Based on that, we generated carrier as cos omega ct plus theta. So here the synchronous carrier is represented as C suffix S of t. Now that multiplier output is already I told you in the BPSK receiver. The multiplier output is simultaneously fed to integrator section and bit synchronizer section. Here using coherent carrier generator, you can generate, what you can do, you can provide frequency or phase synchronization, and you can provide timing synchronization using this bit synchronizer. So bit synchronizer is used for timing synchronization. Okay, so bit synchronizer acts as timing synchronizer because based on the pulses generated, series of pulses generated by bit synchronizer, the switches S1 and S2 will operate. Here the switches both S1 switch you will close before starting of the bit interval. Then the earlier integrated output will be set to 0 and S1, S2 both will be made open. S1, S2 both will be made open during the pulse duration, during the pulse width or of TB, because here symbol duration is equal to bit duration. Both switches S1, S2 will be open. Once both are open, the integrated output will be set to 0. Sorry, integration will perform. When S1 is closed at the starting of the bit, our past integrated data is set to 0. During the bit interval, S1, S2 both are open. Once both are open, the low pass filter performs integration. Okay, so after completion of the bit duration TB, S2 is closed and S1 is open. Once S2 is closed, the integrated data of the corresponding bit will be forwarded to the decision device. Okay, so what this decision device will do, it compares the low pass filter output with threshold. It compares the low pass filter output with threshold. If the low pass filter output, that is the integrated data, is greater than threshold, decay is 1. If the integrated data is less than V reference, then decay is 0. Now, this is the extra element added in the DEPSK receiver compared to BPSK receiver. What you are adding here? You are adding an XOR gate. What this XOR gate will do? Dk is compared with dk minus 1. Already I told you what is dk minus 1. Dk is the received digital sequence, or you can say recovered, reconstructed. You can say it as a reconstructed sequence. Okay, so this dk is compared with dk minus 1. Actually, dk is a unipolar energized sequence, but what is the input? Input is bit sequence bk. So using dk, you should generate bk. So that's why, how can you generate? Once again, use the same XOR gate, so that by comparing dk with shifted dk, what is dk minus 1? 1 bit delay sequence. To get 1 bit delay, you should shift the entire sequence by, you should right shift the entire sequence by 1 bit. So dk is compared with dk minus 1, so that our output will be bk, where bk is the transmitted signal, and dk is the output of differential encoder. So from the output of decision device, you can obtain the unipolar energy, but you should get the original transmitted sequence. Dk is the output obtained from differential encoder, not the transmitted signal. So to recover the transmitted signal dk, what you can do? Dk is compared with dk minus 1. So it both are applied to the XOR gate. Here one more differential decoder is used. What this differential decoder will do? Whenever dk is equal to dk minus 1, bk will be 0. And when dk is not equal to dk minus 1, our output bk will be 1. Okay, when dk is equal to dk minus 1, output bk is 0. When dk not equal to dk minus 1, our output bk will be 1. Okay, now this is all about the circuit of DEPSK receiver section. So what is the main conclusion from this slide? If you observe the circuit of DEPSK receiver with BPSK receiver, here you will have, here in the case of DEPSK, you will have a new element called as differential decoder. Okay, this differential decoder uses XOR gate. This is used to recover the original signal from differentially encoded data. Okay, from dk you need to extract bk. That's why we are using differential encoder, which consists of XOR gate. Okay, so this is about the differentially encoded PSK receiver. So is this like slide okay? Can we move to the next slide? Any one of the student respond? Please, any one of the student respond. Is it okay? Can we move to the next slide? Can we move to the next slide or not? Please respond. K5.
Ma'am.
Is the slide okay?
Okay, ma'am.
Can we move to the next slide?
Yes, ma'am.
Okay, okay, thank you. Okay, let us move to the next slide. So here you can see the coherent detection of DEPSK signal. Already we discussed almost all the same steps in BPSK receiver, but the basic difference in BPSK receiver and DEPSK receiver section is the addition of differential decoder at the receiver section. It consists of XOR gate. It consists of XOR gate. Now already we can say that phase lock should satisfy two criteria. So what criteria it should satisfy? Both frequency or phase synchronization, and second one is timing synchronization. Here frequency or phase synchronization you can provide by using coherent carrier, and timing synchronization is provided by the bit synchronizer. It's provided by bit synchronizer. Now this timing synchronization, if you observe timing synchronization, here this bit synchronizer is able to generate, this bit synchronizer is able to generate the series of pulse train, okay, series of pulse train with the width of TB, with the width equal to bit duration. Okay, so based on the width corresponding bit duration, you can be able to operate the two switches used at the integrator. Now, how can you be able to generate the coherent carrier? Please observe the second point. So you can generate the synchronous carrier which is stable. Okay, so you can generate stable coherent or synchronous carrier by using three steps. Okay, so what are the three steps? Square law device, band pass filter, and frequency divider. Okay, and the generated coherent carrier is applied to the multiplier. Okay, so the multiplier other input is DEPSK signal. So already we discussed all these points in BPSK receiver. So the output of multiplier is fed to the low pass filter and also to the bit synchronizer. Bit synchronizer generates series of pulse train. Okay, so low pass filter performs integration. So low pass filter performs integration only for the bit. Okay, so that's why two switches, the corresponding two switches S1, S2 will be made open during that time. So once both are open, automatically the integration will be performed and the data will be forwarded to the low pass, forwarded to the decision device. Okay, so we can see the mathematical analysis in the next slide. So here bit synchronizer is used for timing synchronization and coherent carrier is used for frequency or phase synchronization so that you can satisfy the phase law criteria. Okay, let us move to the next slide so that you can see the mathematical analysis of DEPSK detection, which you can see almost all, it's almost all similar to binary phase shift keying detection, except that here the received signal DK is a unipolar format, and in the case of BPSK, the B of T is a bipolar signal. Okay, so now please observe the what is the received signal for DEPSK receiver section. The incoming signal is dk into AC cos omega ct plus theta. See, already we defined what is theta. Theta is the phase variation. Theta is the phase variation that that's our assumption. Okay, we are assuming theta as the phase variation that occur due to the noise present in the channel. Okay, and next our assumptions are, let us consider the amplitude of carrier as 1 volt, and we know already the value of dk. So what is the magnitude of dk? Being a unipolar energy, its value is 1, because what is the output of XOR gate? For any XOR gate, the output is 1 for different inputs. Okay, for same input, the output is 0. So that's why it has only two levels, that is 1 and 0. So if it is unipolar emergent, dk is 1 for the input 1 and dk is 0 for input 0. Actually here dk is 0 for input 0. Okay, so what is dk and what is input? Dk is the encoder output. Input is bk. Input is bk and dk is the encoder output. So here dk is 1 for input 1. What is input? Bk. Input sequence to the transmitter is bk. Okay, so for bk 1, dk will be 1, and for input b of t 0, we got dk as 1. dk as 0. Okay, so now anyhow the our differential encoded data is a unipolar only. It consists of only two levels, 1 and 0. So whatever the evaluation we are doing, it is only for the input 1, because for the input 0 the dk is 0. Once the dk is 0, what happens to our the whole magnitude? It will, so if you square, it will become 0. If you square the 0, the output is 0 only. Okay, so whatever the evaluation, it is only for the binary data 1. For 0, the everything is 0 only. So 0 multiplied any factor, it gives you 0. So output is 0 only. Okay, band pass filter do not allow the DC component and magnitude term, but allows only cos 2 of omega ct plus theta. Almost all the three steps remain same as that of BPSK detection. So, so upon eliminating half, so we'll get only cos 2 omega ct plus theta. So here frequency divided by 2 generates the synchronous carrier. Because why divided by 2 from the starting onwards? Because this is a binary transmission technique. Here it is divided by 2. It generates a synchronous carrier which is cos omega ct plus theta. Okay, this is synchronous carrier. Now this is multiplied by DEPSK signal. Okay, so what is DEPSK signal? dk into AC cos omega ct plus theta. If it is multiplied by cos omega ct plus theta, you will get dk into AC into cos square omega ct plus theta. Okay, replace AC as root 2ps. See, the working principle is same as the BPSK. So replace AC as root 2ps. If you replace, you will get dk into root 2ps into cos square omega ct plus theta. But cos square x, you can rewrite it as 1 plus cos 2x by 2. Okay. So it will be 1 plus cos 2 of omega ct plus theta divided by 2. So 2 gets cancelled. Okay, so you will get root ps by 2. dk into root ps by 2 into 1 plus cos 2 omega ct plus theta. Now this output is applied to the low pass filter. And simultaneously it is fed to the bit synchronizer to achieve timing synchronization. Okay. Now let us see the integrator and switches performance. So when switch 1 is closed, switch S1 is closed at t is equal to 0. How can you get these pulses? By using bit synchronizer. S1 is closed at t is equal to 0. The integrator output is reduced to 0. So S1, S2 both will be made open during the pulse width, that is from 0 to TB. So then the integration will perform. Then the low pass filter performs integration. So S2 is closed after the bit duration. Okay, so S2 is closed at t is equal to TB.
ప్రతిరోజు మనం సిలువ వేసుకోవాలి ఈ శరీరం ఆదాము అవ్వ నుంచి కాబట్టి.
Okay, so S2 is closed at t is equal to TB. Then the integrated output is fed to the decision device. Okay, so if you perform the integration at kth interval, so you can get S naught of KTB, which is equals to integration k minus 1 TB to KTB dk into root PS by 2 into 1 plus cos 2 omega CT plus theta dt. This whole factor is nothing but the output of multiplier. So already I said you in BPSK detection that the integration of cosine or sinusoidal waveform for the complete cycle is equals to 0. So that's why integration of cos 2 of omega ct plus theta is 0. So finally you will get dk into root ps by 2 into integration of dt, that will be t. So apply the limits. The limits are k minus 1 tb to ktb. So finally you will get the output of the low pass filter as dk into tb into root ps by 2. Okay, this is about the low pass filter output. Now this is applied to the decision device. So what is the output of low pass filter for BPSK? You will get B of t into TB into root PS by 2. But here instead of B of t, you will get dk, because here you are considering the unipolar sequence. So low pass filter output is forwarded to the decision device, and the decision device compares the low pass filter output with the threshold. Threshold voltage is V reference. Okay, so decision device output is 1 when low pass filter output S0 KTB is greater than V reference, and it is 0 when low pass filter output is less than or equal to V reference. Okay, so up to the decision device, the operation is same as that of BPSK receiver. Then the signal is forwarded to the XOR gate. So what is the received signal? DK. DK is the received signal that is fed to the XOR gate. So what is the operation of XOR gate? To avoid the error bit propagation, the output obtained from decision device, is applied to XOR gate. XOR gate output is BK. So here BK is equal to 0 when DK is equal to DK minus 1. When DK is not equal to DK minus 1, our BK is 1. So output of XOR gate is 1 when DK not equal to DK minus 1. That is when 0 or 1 case, or 1 and 0 case. XOR gate output is 0 when both are same, both the inputs are same. That is when inputs are 0, 0 or 1, 1. Okay, so upon utilizing the XOR gate, DEPSK errors occur in pairs instead of propagating the error to full sequence. Okay, so in the case of DEPSK, here error occur in pairs, not like propagating throughout the sequence. Because you are using XOR gate, this XOR gate reduces the error propagation to occur in pairs. That is, if there is one bit error, if there is a single bit error, if there is any single bit error, that single bit error may cause to disturb only 2 bits, not to the entire sequence, as in the case of DPSK receiver. But in the case of DEPSK, error occur only in pairs. Errors occur in pairs. But in the case of DPSK, error gets propagated. Error gets propagated. So this XOR gate used in DEPSK can be able to reduce the errors, reduce the error propagation. And but here what is the drawback? The error occur in pairs. Okay, so from this slide, so please observe this slide here. So what is the XOR gate output at the receiver? This is the output of differential decoder. Here differential decoder uses XOR gate. So BK is DK XOR DK minus 1. For example, take the DK, okay, reconstructed decision device. So let us take DK. What is DK? Output of decision device. At the receiver I am speaking. So DK, let us assume it as 0, 1, 1, 0, 1, 1, 0, 0. Okay, 0, 1, 1, like 0, 1, 1, double 0. Okay, what will be DK minus 1? Please right shift the entire sequence. If you right shift the entire sequence, the LSB bit, okay, please right shift the entire sequence. So you will get 0, 1, 1, 0, 1, 1, 0, 0. So please shift one bit right. Now take the XOR of DK and DK minus 1. So if you take the XOR of DK and DK minus 1 using the same operating principle, what is the XOR gate operation? For different inputs, what is the first data bit? So 0, you can leave it. Please observe 1, 0, the output will be 1. And for 1, 1, both are same, so output is 0. Next 0, 1, both are different, so output is 1. Next comparison is 1, 0, output is 1. So next 1, 1, so output is 0. For same data, output is 0. Next 0, 1, the output is 1. Next is 0, 0, the output is 0. So like that, you can get the binary sequence DK from the XOR gate, or you can say from the differential decoder. For example, let us introduce an error in the 5th location from LSB or from 4th location from MSB. See, I mentioned with the arrow line. So 0, we are replacing it as 1. For example, instead of 0, we got it as 1. Let us see the operation. So instead of 0, we are replacing it as 1. If we replace it as 1, what will happen? Take once again the XOR of DK and DK minus 1. So because of this kind of XOR gate operation, error occurs only, so 1 bit error, 1 error bit occur only in pairs. So only 2 bits gets affected, not the entire sequence, as in the case of DPSK receiver. In case of DPSK receiver, because we are not using XOR gate at the output, okay, so the entire sequence gets disturbed if there is a single bit error. But in the case of DEPSK, a single bit error will affect only 2 error bits. Please observe the output of BK in the operation of A, and you observe the same figure B. In the figure B, we considered 1 bit error. Please observe the outputs of BK in the section A and section B. In section A, we got it as 1, 0, 1, 1, 0, 1, 0. But if you do the XOR operation for 1 bit error, you can get the output as 1, 0, 0, 0, 0, 1, 0. So only 2 errors. But the error has not at all propagated, as in the case of DPSK. Okay, so what is the DEPSK advantage? Here you can reduce the error bit propagation. You can reduce it to only 2 bits. So in DEPSK, error occurs in pairs. If there is 1 bit error, 2 bits get affected. Only 2 bits get affected, not the entire sequence. That is the main advantage of DEPSK. Okay, next, the remaining portion we can discuss in the next class. Okay, you can leave the class. I took the attendance. Any doubts? K5 చెప్పండమ్మా.
Hello.
చెప్పండి అమ్మా చెప్పండి. వాట్స్ యువర్ డౌట్?
Ma'am, why don't we use XNOR gate at the DPSK receiver section, ma'am?
ఎక్కడమ్మా ఒకసారి ప్లీజ్ రిపీట్ ఇట్ అగైన్.
Why don't you use XNOR gate at the DPSK receiver section?
XNOR. Here actually we are implementing XOR gate. So using XNOR we did not get any output. Please you check it using XOR operation. If you cross check using XNOR operation at the receiver, you don't get the output. ఒకసారి మీరు ఏం చేస్తారంటే బైనరీ డేటా లైక్ మనం ఇందాక తీసుకున్నాం కదా లాస్ట్ క్లాస్లో డిపిఎస్కేకి 001 001 001 1 take the same sequence, and if you apply the same to the receiver section, if you use XOR you won't get the entire sequence. XOR if you replace with XOR gate you will get the output. Okay, XOR యూస్ చేస్తే మనకు అవుట్పుట్ రాదమ్మా. K5 Leela Krishna.
Okay, ma'am.
Okay na? Is it okay or not?
Okay, ma'am. Okay, ma'am.
Okay ma, thank you.